Alright, sorry for the delay there. I was just passing back people's tests. So let the people online know I actually did start class on time, so please don't tell the VCAA on me. Does anybody have any questions about anything before we start? So, got the final coming up. We're going to keep on going chapter 10 for now, and then we'll start doing reviewing. It's going to be nice, actually. You know, we get some review time before the final. So, are your other classes like that, or are people pushing really hard near the end? Is it the smooth, chill end, or is it the upward sprint at the end for you guys?
It's chill here. Yeah.
It's what?
There's no classes where it's rushed for me.
Oh, that's nice. Oh, good. Oh, upward sprint. Okay. This is a tough class, though. Chemistry, if it makes everyone feel better. People really hate Chemistry 161. This is like one of the most hated classes. People probably hate organic chemistry worse, but that's more pre-meds. So about 1/3 of all college students take this class. No, I'm sorry, 1/4. About 1/4 of all college students take this class. So this is a very, very commonly taken class. But anyways, so where we left off, I guess I can back up to we ended here with the VSEPR table and saying what the shapes mean. So let's start using a table to predict some things. What is the geometry and bond angles of PCl3? So in order to do this, it helps to write the Lewis structures. So phosphorus has 5 valence electrons, and where I'm getting that from is phosphorus is right there, and even it's drawn with 5. So 1, 2, 3, 4, 5. 5 for phosphorus. Oh, and chloride. I guess the other one is chloride. 2 more. So 5, 6, 7. 7 for chlorine. So 5 plus 3 times 7 is 26 electrons. So then phosphorus in the center, chlorine's around, so each line is 2. So we place 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Like so. And this one's also nice because phosphorus bonds with 3 and chlorine bonds with 1, so it's not one of the weird ones. Either way, now what is phosphorus? What does it have? It has 4 things around it. So there's 1 lone pair and 3 bonds. So what this means is tetrahedral electronic geometry and pyramidal structure, molecular. What does it say? Bond angle. So it's pyramidal. Which means that these angles here should be less than 109.5 degrees. So, and the reason being, so the perfect tetrahedron is 109.5 degrees, but because there's this big region of negative charge, so it would normally be 109.5 degrees, but with that big region of negative charge, it's gonna move it in a little bit. And let me show you the chart. You will be given this chart. So 4 things: 3 bonding, 1 lone pair, tetrahedral electronic geometry, pyramidal geometry, bond angles slightly less than 109.5 degrees. So because of the valence shell electron pair repulsion, that's what VSEPR is. That outside lone pair is scooting it in. So Does that make sense? Questions with this one? Questions? Okay. All right. Let's do it again. So geometry and bond angles for ICl4 minus. Iodine and chlorine, they're both halogens. So it's 5 times 7. There's 7 valence electrons in the halogen, and plus 1 from the minus 1. So this is 36 electrons. 5 times 7 is 35, plus 1 is 36. So we have iodine in the center, and there's going to be 5 chlorines. I don't know what the structure is. I'll just put 5 around.
Is there 4 chlorine?
4. I'm sorry. You're right, 4. Jeez. Oh. Thanks, Will. I messed that one up. Oh, it's still 5. I'm sorry. It's still 5 times 7 plus 1 is still 36. Okay, and then there's iodine, Cl, 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 Cl. Okay, so we need 36 electrons. 4 lines, that's 8. 10, oops, too many. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So is that right? So 4, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23, 24. Yeah, that's right. So this has, so iodine, there's 8 things. I'm sorry, 6 things. What am I saying? You know what? I'm going to take a chocolate break.
Power up.
Making 2 dumb mistakes. Time to eat chocolate. All right. Until the sugar hits me. Whew. All right, so iodine has 6 things. 6 things. There's 2 lone pairs and 4 bonds. And this means octahedral geometry. Electronic, I should say, electronic. And the molecular is going to be square planar. And that means that there's going to be iodine in the center with chlorines around it. And then above and below is going to be a lone pair. Like that. So you have the chlorines and the iodine all coplanar with 2 lone pairs above and below. And the bond angles are then going to be, this is going to be perpendicular. They're all going to be perpendicular here, so this is going to be 90 degrees. And then with this other one here, 180 degrees between the 2 lone pairs. So where am I getting that? You don't have to memorize this chart. I have it memorized. So 6 things for bonding, 2 lone pairs, octahedral, electronic geometry, square planar, molecular geometry. So again, you get this chart. So you don't have to memorize it. Questions though with this? Oh, I'm feeling the energy already. Ooh. Love me some chocolate. Okay, so that's all fun and good. What about a bigger molecule? So let's look at methanol, and let's predict the geometry. So CH3OH, well, let me count up the electrons. Carbon has 6. Hydrogen has 1. Jeez. It does have 6, but has 4 valence. Oxygen has 6. So it's 4 plus 6 plus 4 times 1. So there's 4 from the carbon, 6 from the oxygen, and then there are 4 hydrogens. That is 14 electrons. So carbon is going to be attached to oxygen, and carbon tends to bond with 4, and oxygen tends to bond with 1. Besides the fact, if you look at this CH3OH, that's what it means, exactly what I've written there. So that's the CH3OH. So let's count the lines. We have 5 lines. 1, 2, 3, 4, 5. 5 lines means 10 electrons. So we need to place 4 more. And look at carbon. Carbon has 4 lines, that's an octet. Oxygen has 2 lines, that's 4 electrons. It needs 4 more. So we place the other 4 electrons around oxygen. We give it the octet. Now we've placed all the electrons. So with this molecule here, though, so let's talk about the structure. This side here is tetrahedral, and the angle here, this is going to be 109.5, and this side here, this is going to be bent because of the, so oxygen has 4 things, so 2 bonds, 2 lone pair. This means bent. It's a bent structure. So, well, actually, this is going to be a little less than 109.5 because the oxygen's got it's a bigger electron group, so it's going to squish it down. But the bond angle here is going to be about 109.5. Even when it squishes it down, it doesn't squish it down by that much. It's only a couple degrees. And then this section here, this is going to be bent. And this is important because all bent molecules are polar. And so methanol with the OH group here, this OH group is going to make this molecule polar, which we're going to talk about soon. But when you do this, when you look at a molecule and it has different parts, you have to look at each piece individually. So if to the carbon, it's tetrahedral because it's got hydrogens, 3 hydrogens, and an oxygen all bonding. And the only difference is that this oxygen is a little bigger than the hydrogens. So it's tetrahedral. Or in this site, for the oxygen site, so the oxygen sees a hydrogen and another group. So it sees a hydrogen and another group over here. So to the oxygen, it's like, oh, I'm bent. So, and whereas the carbon sees it kind of like, I don't know, like warrior, is this 2? I don't know, my yoga poses. So it sees it as having 4 things. Okay, questions with this? Does anybody do yoga here? No one does yoga, okay. All right. So let me see if you're following. What is the shape of ammonia, NH3? So I have abbreviated the chart here. The number of things, the bonding groups, the lone pair groups, and then the molecular geometry. So geo is geometry, molecular geometry. So we have ammonia and ozone. So what is the shape of ammonia? I'm going to think A, linear. I'm going to think B, bent. I'm going to think C, pyramidal. Okay, most people are going for pyramidal. So it is pyramidal. And because, so there are, for this one, there are 3 bonding. one lone pair, right? So to the nitrogen sees 3 bonds and 1 lone pair. So 3 bonds, 1 lone pair is a pyramid. Right there. Okay. So how about ozone? How many think it's A, linear? How many think it's B, bent? How many think it's C, pyramidal? How many think it's D, tetrahedral? So let's look at ozone. So how many things are around ozone, or the oxygen? Let's look at what about this central oxygen atom? How many things are around it? So there are 3 things. There are 3 things. There are 2 oxygens and 1 lone pair. So the single and double bond doesn't matter. It just sees 2 bonded oxygens. So it sees 2 bonded oxygens and a lone pair. So do you guys see that? Some people think it's linear. How many think it's bent? How many think, oh, so it is bent. Some people are still confused. About half the class is going for it. I mean, do you see this? So the oxygen, here is the center of my universe is the oxygen. And, oh, it's got a heart. It's got a heart. The center of my universe is actually a white heart. Aw. Do you see that there? You can't see that. Ah, that's relief. So this oxygen sees a lone pair, and it sees a bonded oxygen and another bonded oxygen. So it doesn't matter the single or double bond doesn't matter. It just matters that there's a group there. There's a atom there. So you see that black oxygen with the heart there sees 3 things. So do you get that? It doesn't matter if it's single or double. All it notices is that there's 3 things. 2 of them are bonding. 1 is a lone pair. Therefore, it's bent. Is this making sense? Does anybody have any questions? I don't know how much better to explain it, though, if you're confused. Okay. Everyone good with that, then? And so I mentioned this before, but the next part of it is when you talk about if molecules are polar or nonpolar. So we have here, so this is hydrogen chloride or hydrochloric acid. So, and hydrogen is attached to chlorine, and the thing is, chlorine is a more electronegative element. So it's really easy to remember. If it's the same elements, they have equal electronegativities. If there are different elements, there are different electronegativities. You don't have to look at, you don't have to have the chart. If they're a different element, they have different electronegativities, which means electrons are going to flow in one way or the other. In this case, the electron density flows towards chlorine. So it's the hydrogen here has a +1 center. The chlorine has an apparent +7 center. So these outside electrons, at least outside for chlorine, there's only a proton for hydrogen. The electron density gets drawn towards chlorine. So as it's drawn this way, there becomes a partial positive side, or a partial positive charge on this side of the molecule, a partial negative on this side of the molecule. And what do I mean by a partial? I mean less than 1.6 times 10 to the minus 19 coulombs. That's the charge of a proton or negative charge of an electron. Okay, so this charge, this partial charge is less than that of a proton or electron. And remember, electrons are this fuzzy cloud. It can move in many different places. It could be in many different places at once. So it's a cloud, and it just kind of hangs around the chlorine more. So then the hydrogen. So this electron's like, you're cool, hydrogen. I like chlorine more, but since I can be in many different places at once, I'm gonna split this partnership 60-40 or something like that. This is like a bad deal. So it's a bad deal for the hydrogen. Chlorine gets a better deal. So, and since there's only and because of this, since there's only 2 atoms, this arrow with that line there, this just means electron density flows that way, and we have a polar bond, and we have a polar molecule. So okay. Oh, and there's there. So what I just said. Now let's look at a different molecule, carbon dioxide. Now this is a linear molecule. 2 things. It's drawn linear as well. So here, the electron density, oxygen is more electronegative. Actually, like I said, it doesn't matter. You don't have to know that. Since these are different atoms, there's a disparity in the electronegativity anyways. So it could flow towards the center. It would be the same thing. But okay, so the electron density flows towards the oxygen, making this a polar bond. And the electron density flows towards this side, making this also a polar bond. But since there's an equal amount of pull in both directions, actually carbon dioxide ends up being a nonpolar molecule. So, meaning that this molecule, carbon dioxide, is not charged. HCl is charged. And CO2, though, is not charged. It has an overall, it's very symmetric. The electron cloud around carbon dioxide is extremely symmetric. It doesn't have any concentrations or gaps in it. Whereas hydrochloric acid, HCl, there is a disparity. The electron density flows much towards the chlorine end of the molecule, make the chlorine end really negative and the hydrogen really positive. So, and when you draw these arrows, so it's an arrow going this way and there's an arrow going this way. I don't know, have you ever studied vector math before? So if you have a vector like this and it's up and down, they cancel each other out. Or so this is the y. The top one is the y-axis. So if you have a vector going up and a vector going down, they cancel each other out. Kind of like there's gravity. So my center of mass, there's 265 pounds of force going this way towards the center of the Earth, and then the floor is pushing the normal force. Normal just means perpendicular, so the normal force is pushing back at 365 pounds. Therefore, I'm not moving, right? The vectors cancel, so I have no net movement, right? But if air doesn't have, there is a normal force of the air, but there's not that much. So if I start up at a higher point, there is a net. There's not the air is not pushing back, so I just fall. Well, I guess the air pushback's a drag, but that 6 inches that I jumped is not enough to have that much of a drag, anyways. So okay, and the same thing. So this is up and down. Same thing if I lean against the wall, right? I'm pushing on the wall right now, and the wall pushes back at the same force that I'm pushing back at. So it works left and right as well. And it can be unequal, right? So I can push myself off the wall. But that's the unequal. The unequal is when I push it and one arrow is stronger than the other one pushing back. Well, I guess that way when I pushed on it, the wall pushed me back harder. So that's the action-reaction law, if you guys know physics. That's physics, I know it's not chemistry, but it's easy to explain the vectors this way. Okay. Now let's look at water. Looking a little busy with water. So water here, here's the hydrogen, the hydrogen. Water is a bent molecule. And so the electron density flows towards the oxygen. So an electron density flows this way. So this is a polar bond. But if you look at the vector, so it's bent, we have the arrow pointing this way, and we have an arrow pointing this way. And this diagonal arrow is, you can break it up, so an arrow going this way, you can break it up into a component this way and a component this way. And if you have two of them, so there's a component this way, a component this way, the ones, so this arrow pointing this way and this arrow pointing this way, these arrows cancel, but the ones pointing up, they add, so the middle ones cancel, but then the vertical ones add, and you get a net vector pointing upwards. So from this, there tends to be a buildup of negative charge around the oxygen of the water molecule, and as such, water is polar. So you're like, what? So what? Why do I care if a molecule is polar or not? Generally speaking, polar molecules will mix with polar molecules, and nonpolar molecules will mix with nonpolar molecules. So you probably know already that gasoline and motor oil, they mix with each other, but they don't mix with water. Or like olive oil. So you can, I cook with the Mediterranean blended oil at Costco. It has grapeseed oil, canola oil, and olive oil. Okay, those all mix. You put it in water, they separate. So oils are nonpolar, and water is polar. And most people think, oh, oil hates water. Actually, oil loves water. So if you look at, here's my artist impression of an oil molecule. They're long nonpolar molecules, is what oils are basically. And water, I'll make it blue. Water is like little V's. Here's my oil and water hanging out party. And water at the tip of the V has a negative charge and a positive charge down there. So let's say you are some random electron here in the nonpolar molecule. What are you more attracted to? Are you attracted to the nucleus over here, this molecule, or are you attracted to the partial positive charge of the water molecule? Which one do you like better? You like the polar molecule. Oil would much rather bond with the water molecule. Water's a jerk. Water goes, hey, you're getting in my way. Water actually, it tends to arrange itself like I've drawn. I've purposely drawn water all kind of going like this. Water tends to arrange itself so that the positive and negative ends align. So, and if you mix oil with water, what does water do? Like, it's saying, you're in my way, you're blocking my bonding scheme, and it pushes the oil out of the way. So water pushes the oil out of the way, and then because we're in gravity, the oil is less dense than water, it floats to the top. So that's okay. So that's why we care, because certain things mix if they're polar, and certain things mix if they're non-polar. And that's a generalization, though. There are some things that can mix both. Ethyl alcohol, so ethanol, can mix both polar and non-polar. So can isopropanol. Methanol will only go in polar. Okay. So how do we do polarity? So, okay, draw the Lewis structure, determine if there's polar bonds, and then look to see if there is a net dipole moment. So let me summarize that for you. I'll make it easy. All bent molecules are polar. all pyramids, polar. It doesn't matter what it is. Ozone, we just learned, is a bent molecule. That's polar, even though it's all oxygen. All bent molecules are polar. Now, if a molecule is linear, planar, or tetrahedral, it depends on how it's connected. So if you look at, so let's start with linear. So as discussed, carbon dioxide, this is a linear molecule, and it's the same on both sides. It has an oxygen over here, an oxygen over here, and then, so the carbon, oxygen, the electron density is being drawn out equally, so the vectors cancel, and makes carbon dioxide nonpolar. Say instead we have hydrogen cyanide, so there's a nitrogen here, and here's a hydrogen. What happens is the electron density is drawn over here differently. Actually, for hydrogen, it's drawn towards the carbon, but it doesn't matter. It's the fact that there's two different atoms. So since there's two different atoms here, this linear molecule is polar. So it lets you know molecules that are nonpolar are very symmetric. When there's a break in the symmetry, then the molecule is polar. Is that making sense? Okay. So let's move on and talk about planar. So here is a planar molecule, boron trifluoride. All the same atom. Each of these are the same. And if I drew the vectors, they would all cancel each other out. Therefore, this molecule is nonpolar. Here is formaldehyde. Here, still planar geometry, but there's a different atom. So hydrogen, hydrogen, different atom, oxygen. Since there's this different atom, this molecule is polar. So, and it's because there's a buildup of, then the electron density would build up around the oxygen. This would be a negative end, this would be a positive end. You don't have to know which end is negative and positive. You just have to know that it's polar. And so you just have to know that these are different, therefore this is polar. So, questions with this one? And so here is tetrahedral geometry. So let me do a simulation for you. Here's tetrahedral geometry. Here is methane. Okay, so 4 things, all the same. Methane is nonpolar because these are all the same. If I were to put a different group here, this molecule now is polar because it's different. Well, I guess maybe I'll put that one back. So this is another trick. This molecule is still polar. So when you look at this, do not do this. Do not say, okay, there's an arrow here, and there's an arrow here, and then they cancel each other out. So don't forget that the 4 bonds, so this is a Fisher diagram, which means that the fluorines are actually like this, and the hydrogens are like this. So since the fluorines are like this, this side will cancel, but they'll have an overall this way. So it's a tetrahedral molecule. So don't think it's a square. If it's a square planar, yes, that would work. But this is not a square planar molecule. This is a tetrahedron. So difluoromethane is polar. Trifluoromethane, polar. Tetrafluoromethane, nonpolar. They're all the same, right? So trifluoro 1-chloromethane. This molecule is polar. because one's different, right? So are you starting to see the pattern? So the pattern is all bents and all pyramids are polar. Easy, no questions asked. If it's linear, planar, or tetrahedral, if they're all the same atom, all the same group, it's nonpolar. If one is different, it's polar. So, make sense? Okay. Now, if you were to do bipyramidal, you would have to look at the linear molecule and then the planar molecule. The planar, so the linear and then the planar. So you would have to determine each of that individually. If the linear is nonpolar and the planar is nonpolar, then the whole molecule is nonpolar. So you could have a circumstance like this. So this is not a question that's fair for the final, but actually maybe I'll do this. Maybe you have a molecule like this. We have a chlorine. So this is the three fluorines are in the plane, and they're all the same. So the equator, the equatorial position, that's nonpolar, and then the chlorines above and below are the same. Therefore, then that's nonpolar along the axial positions. So that molecule as written is nonpolar. Okay, because all the bonds, even though that's not a very good example, because there's actually, I guess there would be an even number of electrons. I guess that one could work. Okay, so that molecule as written would be nonpolar because it's nonpolar along the equator, the planar part, and it's nonpolar along the linear part, the axial part. So you have to look at those two individually. But it's not going to be a question on the test. We're not going to go above tetrahedral in geometry. In octahedral is the same thing. So octahedral geometry, if every single group is the same, it's nonpolar. if you have an octahedron, let's see here. So sulfur. This is a made-up molecule. It would never work. If you had a group here that's different, this molecule would be polar. If you have the same group above and below in the same line, it's nonpolar. So because the sulfur and the fluorines are all coplanar, and then above and below they're the same, so that way it would cancel. If you had this circumstance, we had a fluorine here and a hydrogen here, this molecule would be polar. So because the different groups are at 90 degrees from each other. So 180 degrees, they'll cancel each other out, but if they're 90 degrees, they won't cancel each other out. So, but that's more advanced in this class though. So, but I just explained the logic. Okay. Questions with this though? All right, determine if ammonia is polar. So as already mentioned, ammonia is a pyramid. So all pyramids are polar. Therefore, this is in fact polar. Right? Sound good? And I mentioned with polar, non-polar, it's not just what it'll mix in. Having a molecule be polar has other effects too. The spectroscopy of it. So polar molecules tend to be very powerful greenhouse gases, for instance. So because if you have a separation in charges, they absorb better in the infrared spectrum. So if you look at water, for instance, H2O water is a very powerful greenhouse gas because it's got a negative end and a positive end. It absorbs lots of infrared light. And if you have a molecule like carbon dioxide is nonpolar. It is a greenhouse gas, but like so carbon dioxide is a linear molecule. And remember we talked about the electromagnetic spectrum that the infrared light makes molecules vibrate. So carbon dioxide, it can vibrate. So this is called a bending mode, like this. This is called a symmetric stretch, and this is called an asymmetric stretch. So there is a absorption spectrum for infrared for carbon dioxide, but it's not nearly as powerful as water. So if you ever studied like global warming potentials, if you've seen that, they'll say like, oh, methane is 20 times that. But you look at like a polar molecule like a CFC, that's a polar molecule, it's like 10,000 times as strong as CO2. It's so big because it's polar. So it's just a much better effective greenhouse gas because it's, like I said, a polar molecule. Okay, but that's for future classes. Okay, now I want you to look at these molecules, and these are all coplanar. So these atoms, they're all coplanar. I know that if you look at the carbons, that it has that you have the carbons attached to another carbon, and the question is, so there's two planes. Each carbon is a plane. Are they all coplanar, or could they be bent? Because you could have two planes and they're bent. They're all planar. So these are all flat molecules. So these are all really flat molecules. And I want you to tell me if these molecules are polar or nonpolar. Using this vector kind of stuff I've been talking about. So the first one, this is 1,2-dichloroethene. So you don't have to worry about the names. Oscar does because he's in organic chemistry. You probably covered that first thing, right?
Ethenes was the last. No, last test.
Okay, but did you do naming first?
Yeah, well, we did the naming for alkenes when we did the alkene reactions.
Oh, really? Okay. Oh, I taught it differently. I taught the names first. Okay, so 1,2-dichloroethene. How many think this is polar? How many think this is nonpolar? So we have a split here. So we have a vector pointing this way, and then we have a vector pointing that way. The question is, do these vectors cancel? And they do cancel. This molecule is nonpolar. So do you see the reason why, though? But because actually this one is a lower one that's pointed towards this way. So this is a flat molecule, and there's electron density being pulled towards this chlorine, and electron density pulled towards this chlorine. But so since they're on the plane, these ends, they cancel each other out. So, and the other one, actually the hydrogens are pushing towards it. But even if they push it away, because they're the same on both sides, these actually do cancel each other out. Oh, I forgot to mention, this is also known as trans. This is trans 1,2-dichloroethene. Do I talk about cis and trans? Oh, I do. Yeah. Okay. So trans is nonpolar. Is this making sense? Does the vectors cancel each other make sense? Questions with this? Okay, how about this one? Trans 1,fluoro-2-chloroethene. How many people think it's polar? Okay, most of the class is going for that. It is polar. And the reason being, here I'll make it a fatter line. Even fatter. So fluorine has this big honking arrow that way, and chlorine has an arrow that way. Because the magnitude of this draw is greater than the magnitude of that draw, we have an asymmetry which makes this molecule polar. Does that make sense? Okay, how about this one here? So 1,1-dichloroethene, last one. Some people think this is polar. Some people think it's non-polar. Some people are playing for polar. Are you guys just, I have an arrows here. So what's going to happen here? Are these going to add in? So think about water. When you have something like this, how the components work. Somebody think this is polar? Raise your hand. Okay. Some people are. This is polar because you get a net arrow this way. I'm getting. Maybe I'll use a different color. So you see this? So all coplanar, these opposite arrows, they cancel each other out diagonally. So the diagonal arrows will cancel each other out. If you have the same situation with a different element, one's going to be stronger than the other. So therefore it's polar. So this is non-polar because they cancel and they're all the same each side. Different element, one's not going to cancel, it makes it polar. This, since they're on the same side, the components up and down are going to cancel, but the ones left and right will add. So, is this making sense? Questions with this? So, you say you understand it, but then you're not doing the chem quiz. You actually, please feel free to ask questions. I don't want to. Nope. Okay. I'll trust that you know it then. Okay. So, and I mentioned cis and trans. So cis and trans. So if you have two groups on opposite sides, this is known as trans. If you have two groups on the same side, this is known as cis. Okay, and so what? Have you heard about margarine and other hydrogenated oils? They have those evil chemicals called trans fatty acids that are so bad. Why are we worried about trans fatty acids? So what is a fatty acid? So okay, the way that all plants and all animals store fat is by a triglyceride. So glycerin, it's 3 carbons, and then and 3 OHs. So if there was another OH here, it has a fatty acid attached to it. But if this was an H, this would be glycerin. Okay, so you can buy it in food stores. You can eat it. So you can also use it as a lubricant. So and it's known as a humectant. It draws water to things. So you put it in like shampoo, for instance, and glycerin soap. Glycerin soap has it draws water to it, so it helps hydrolyze things. Okay, so all plants and all animals here on Earth, we store our fats as triglycerides. So that means we have a fatty acid. What is a fatty acid? It's a long chain hydrocarbon attached to what's called a carboxyl group, a C double bond OOH. But then instead of that, instead of the H, it's attached to this glycerin. Okay, and tri mean there's 3 of them. You can also there's some. This is how I did say all plants and animals do this. There's emulsifying agents in milk that have 1 or 2 of these. If you wonder how fat can dissolve in milk, it has like 1 or 2. So instead of triglycerides, some of them have 1 or 2 fats in there, so it makes it easier to dissolve it in water. So if you wonder how you can have the fat and stuff in milk, it's because of one or two of these. Okay, and also all fats for all plant animal here on Earth, they're all cis bonds. So that means if you have a double bond, they kind of fold in on each other like that. So so triglyceride, this is flat. The molecule actually kind of looks like this. You'll have a line, but then you'll have these fats sticking off, but they'll kind of form like, it is almost like a three-legged kind of claw-looking thing. It'll be like a knotted claw too, and they'll be as far away from each other as possible because they're negatively charged and they want the electrons repel. So this is what a fat really looks like. You can't see them because light's much larger than atoms are, but this is what it would look like, and they all kind of knot in on each other. So when you hydrolyze fats, you add acid to it. So like you take something like olive oil and you want to hydrolyze it, you heat it in the presence of acid. You can do it with vinegar, or more commonly hydrochloric acid. And what happens then is that the acid can break some of the double and triple bonds and turn a triple bond into a double bond, turn a double bond into a single bond, and it'll add hydrogen across it. So if you have a triple bond that turns into a double bond, what happens for hydrogenated oils, they become both cis and trans. But they're slightly more likely to become trans. And the difference is our body is programmed chemically to handle cis only. So if you introduce trans, it's something new, and our body has to turn it into cis to use it. So, and that takes effort, and it puts more stress on our system. So that's in essence why trans fatty acids are bad. So it's it's a little tougher on our system. Okay. And I already mentioned this, that oil and water do not mix. Not surprising. And I already mentioned the reasons for that. The polar things tend to mix with polar things. Non-polar things tend to mix with non-polar things. Also, salts will only dissolve in non-polar solvents. So you cannot get salt to dissolve in gasoline. So there has to be a polar bond for a salt to bond to that. But you can get water and oil to mix. And it is an ever magical substance called soap. So soap is a substance that can cause polar and non-polar things to mix. Soap is actually extremely magical. I mean, chemically speaking, it was invented in Egypt. In ancient Egypt is where we discovered soap. And another fun fact, all soap is antibacterial. So there was a series of laws passed in the late 1990s. In order for something to be called antibacterial, you had to have an antibacterial agent in it. And there's a list of chemicals that the government says is antibacterial. So bleach is one of them, and triclosan is another. So suddenly, a lot of laws changed and like labeling changed. So it's funny. I remember I was working for Bath and Body Works at the time. I was working in their legal department. I was looking at their labeling. I was an intern, and I was working on their labeling with their labels, and the laws changed to say what's antibacterial and what's not. And I think I didn't know about this, but food also seemed to change because suddenly you had things like high fiber popcorn. I mean, popcorn has always been high fiber. The fact that the government says you can call it high fiber now doesn't mean anything. So, but soap always is and always was antibacterial. But if you buy an antibacterial soap, it means it has one of the antibacterial agents that the government says that it's, at least the U.S. government bought soap in the United States. It can be called antibacterial soap if it has one of those agents in it. You don't have to prove that that agent is what kills the bacteria. It just soap kills germs. But there's been also new studies. There's an emerging field right now with a microbiome. Are you familiar with the microbiomes? We talked about it a little bit before. So, like I said, it's an emerging field, but we're starting to look at how our symbiotic relationship with our bacteria is and how that can affect your overall health. So part of our immune system is our microbiome, and part of our GI tract is also our microbiome. It's everywhere. So, and we have a relationship with it, and it's mutually beneficial. And the question that we're having is, do these antibacterial agents, are these altering our microbiome? The answer is yes. What's the effect of that? We don't know yet. Okay, but let's go back to soap. Let's say you're making Thanksgiving dinner, and I like to put olive oil on my turkey before I put it in the oven. And if I'm rubbing olive oil on, I've got olive oil on my hands, okay? So I can take a paper towel and I can rub it off, right? I can rub off the olive oil, but even though I still it's not like I rub it off and oh, okay, time to go, touch my face now. I still have that kind of film of oil on it that feels dirty. Then I'm like, you know what? I'll just, and you can mechanically pull it off. You can, if you take enough paper towels and you rub your hands and stuff, you can get rid of all the oil. So you can do that. Or you can go and you can use soap. But when you use soap, what do? Do you put soap in your hand and say, all right, soap, do your magic? No, you put soap in your hand, and then you take water. So you put soap in your hand, and then you take water, and then you rub your hands together. So for soap to work, you need soap, you need oil, you need soap, and you also need the mechanical motion. So rubbing your hands together does something. So just like your laundry machine, your laundry works on the same way. Your laundry machine rotates back and forth. So you need the agitation to do that. So what you're doing, you're making micelles. It's said like this. So a micelle, and what a soap molecule is. So this is the cheapest and simplest kind of soap molecule. This is known as an anionic surfactant. So it's anionic because the end is an anion. So, and has anyone ever made soap before? I have. The way you make soap, have you ever seen the movie Fight Club or read the book Fight Club? The book is much better than the movie, by the way, if you ever read the book. It's hilarious. But anyway, the way you make soap is you take fat, Castile soap. If you heard of Castile soap, that's animal. I'm sorry, it's plant. It's plant-based fat. It's Castile soap, and most soap though is made from animal products. You take fat and you melt it, and then you throw lye, L-Y-E, sodium hydroxide in it, and then it does the saponification reaction. It rips the fatty acids off of the glycerin. So triglyceride rips the acids off of the glycerin molecule, and you're left with glycerin, and then you're left with the sodium ion, sodium plus ion, and it's then the fatty acid with the anion on it, with the C double bond O minus on there. So usually known as stearic acid. That's a generalized fat from animals. So it's sodium stearate. If you ever see sodium stearate, that's the most commonly used soap there is. So, and it's a saturated fat because it's animal-based, so it's all saturated. So that's why it's a straight line. So you have a negative end and a long nonpolar end. This is an anionic surfactant. You can have cationic surfactants. Those are a little more caustic. You can have non-ionic surfactants, which don't work very well. And you can have amphoteric surfactants, which are both positive and negative, depending on the pH. They're expensive. So, but that's the cheap stuff. And what happens is, so this like I'm drawing with a head and a tail, that's a single surfactant molecule. And what they end up doing is the tail will preferentially go towards each other, and the heads will point away, because the tails are nonpolar, and they'll mix with nonpolar things, and the heads are polar. and it forms a three-dimensional structure. So an oil droplet, so if you have an oil droplet, and the soap molecules, the surfactant molecules, the tails will surround the oil droplet, and then the outside will all be the negative anions. And then now that whole thing, this whole thing is called a micelle. Now that micelle can then dissolve into water. But you need to form the micelles. That's why you can't put soap on your hands and put water under your hands like, oh, I'll clean my hand. No, you have to rub it together. When you're rubbing it together, that mechanical force is making the micelles. And then you can get all the oil off of your hands. So you biology folks, if you get two of these together, if you have two groups and you have a negative side and then you have two layers of something with a negative side on both ends, what does that look like to you? There's a certain structure.
Bilayer.
Bilayer, which is
Cell membrane.
cell membrane. What is a cell membrane made of? Phospholipid bilayer. So phosphate, PO4 minus 3. So that's what a cell membrane is. It's a phospholipid bilayer. So you have a phosphate group attached to a lipid, and you have two of them, a bilayer. And that is how cell membranes work. That way your cell membrane is only 2 molecules thick. So, but you have outside of the cell membrane, you can have water outside the cell membrane. Then you have this barrier that's 2 molecules thick, and then you have the inside of the cell, the cytoplasm, which is also aqueous. So, simple 2 molecules are what separates your cell from its inside and its outside. And the organelles inside the cells have a similar bilayer as well. Other applications is obviously biology. You can create something called a liposome. You can encapsulate. They say encapsulate. You can encapsulate things like nutrients inside of a liposome. It's like a bilayer. It don't have to be phospholipid, but it can be stearates or something like that. You can encapsulate certain things inside of each other. And you can even have micelles in micelles. So you can have inside the oil, you can have what are called reverse micelles, where you have the phosphate group on the inside and a lipid outside. And you can have water aqueous environments suspended inside of an oil droplet inside of a micelle. You can do that in plain old oil, or you can do that, or it could be inside of a micelle itself. So it's like a micelle within a micelle. So it's almost like the computer program. Are we in a simulation, or are we in a simulation within a simulation within a simulation? Simulation kind of thing. Okay. And this is a chemistry joke. Does anybody know what this is? This is transparence, because it's ma and pa in the transposition. So this is one reason not to be a chemist, is that our humor is terrible. Right, so that's transparence. Ha 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 ha. All right, so we are done for the day. Anybody have any questions? Okay, well, I shall see you then on Wednesday.